You're welcome.
All right, welcome. Thanks again, Florian, for giving this nice talk. And so it's something really I can kind of build up on and extend this. And in short, I will try to convince you that your outlook on uncertainty in machine learning should be like this. It should be bright. We should be aware of it, but it should be bright. More or less, this boils down to not only using point estimators, but really assess whole probability distributions. And an often coined phrase is that machine learning applications are more moving from the lab to the machine room. So what I would consider a lab situation is that you just have a hammer, which is supervised learning, and most problems really look like a nail. And once you've solved a problem, you have good prediction accuracy, you think you're done. But actually, I mean, what often happens, the problems kind of call for a recommended action. For example, placing orders whatsoever. And I will start off with basically just two examples that illustrate that. The first one being a sensor fusion example. So imagine complicated machine with thousands of sensors, and you just want to know, when do I have to send a mechanic? Because the machine will fail or is going to fail with a certain probability. So, well, in the past, before machine learning, problem wasn't really feasible because it was hard to get a prediction on the failure. But I mean, with machine learning, it seems like, okay, you only need a good prediction for a failure. But I mean, what are you going to do if you predict a machine is going to fail in one location and another one is going to fail in another location? So you have to kind of find the mechanic's traveling route at the end of the day, which kind of would make up the ultimate data science pipeline. You have your supervised learning for sensor fusion plus some optimization step for route. I mean, it's quite a complicated problem, but this would be the ultimate goal, basically. And I mean, this is an example I choose because it's clear that probability matters. So, I mean, if one machine is going to fail at a probability of 0.9, you want to send the mechanic first as opposed to a location where a machine is going to fail at a probability of 0.6, for example. So let me move over to a problem we're quite familiar at Blueyonder, which is grocery replenishment. So this is one of our products. And real problem is that you want to place orders for a grocery store. So again, I will go back into the past or even conventional algorithms nowadays. So the essential thing was basically the demand prediction algorithms were limited and only worked fine in special situations. But what would you do if, right before Christmas or inside a promotion? So this is where machine learning comes in and where you can improve your demand predictions very much. So, and what most people think, and what I thought a couple of years ago when I joined Blueyonder, well, that's the essential part. Everything else is trivial. You just need good demand predictions. It turned out I was wrong, and during the past years, we've seen also the parts that come after the demand prediction to become more sophisticated. So what you need is actually an optimization step that really tells the store manager or whoever does the orders what quantity to order, how many pieces to order. And this also means, okay, probability matters. Because, I mean, might be a rare event and you run a high risk of selling much. So this is the point I'm going to make. So there's two steps to it, basically. First one, going beyond a point estimator. The second one, using an optimization behind your machine learning pipeline. So what about first step? And here I can just build on the previous talk. So differentiating different kinds of uncertainties. First of all, the epistemic or model uncertainty, which is something you could minimize in principle if you have more data, if you had chosen a more suited model, whatsoever. So I will assume that he has this under control and that is more or less negligible for the rest of this talk. So I don't have to care about the uncertainty split, basically. And on the other hand, we have the things we just can't learn with a given data. So basically pure noise, which is uncorrelated to the input variables. So, I mean, there's two ways of dealing with it. I mean, one way is seeing, okay, you realize you just want to go ahead with your data set. You see it's highly noisy, and you realize you will be stuck in improving the prediction accuracy. You can't do anything about it. So it's, yeah, you realize you see it as completely lawless. This is what you end up using a point estimator, basically. However, there might be some lawfulness to it. And, I mean, often the uncertainty statistics or the noise statistics varies with certain input features. And this is often highly correlated, and that is something you can learn in principle. So it boils basically down to predict the probability distribution. And here I have just plot an example. This is what you attempt, basically. You want to predict these error bands, for example. So again, as Florian did, I will come back to a linear model because it's easy, because I can just show the whole data set in one plot. So we have simple signal, and we have some Gaussian noise on top. And I mean, we have to address that the noise width increases with the input variable. So I will also be assuming that you have basically limited amount of time, so that you're just trying to set up the data science pipeline quickly to get a first shot. So you might be trying to use a scikit-learn stack, and yeah, you want to go for quantile regression. And you pretend you're completely agnostic about the noise, so you really want to learn the noise statistics. So and here comes the scikit-learn example. I would just contrast. I mean, what you usually do is kind of predict the mean of the noise distribution you're gonna end up with in this example. Yeah, the mean is minimized by a least square function. So you just put the least square for a loss function. So again, this is just for demonstration purposes. It's a little bit of an overkill here. I didn't do any hyperparameter tuning. It's really just demonstration here. So when I predict the quantiles, well, for this regressor, and that's to my knowledge the only one in scikit-learn currently, I just can replace the loss function, and I can give a quantile. So Florian explained how this loss function looks like and how it comes about, and I just can have an estimator for my quantiles, for any quantile I like. So I'll come back to the fact that this is not fully supported in scikit-learn later. So, but I'm first going to show you the results. Okay, this is first shot. I mean, simple problem, but doesn't look so bad. So I'm completely agnostic of the noise distribution function. So I learned that, okay, I can improve a little bit. It should be symmetric. It is not really, but still. But what I did here is only predicting two quantiles. That's enough to plot an error band, right? But I mean, if I really want to learn the whole probability distribution, I'll end up predicting 30 up to 100 quantiles. So, and again, this, I mean, if you do this on a large scale, this can also result in high CPU consumption. So you might want to find ways around, depending on the size of your problem, or if you're in the cloud and if you have cloud costs. And there's also another downside to it, what I mentioned. It's not really supported in scikit-learn. So this is basically the only estimator supporting it. There's some extensions like scikit-garden supporting quantile regression out of the box. There might be soon an extension package offering some standard algorithms, but still you might end up implementing stuff by yourself, which, if you have no time, slows you down a little bit. So the next thing is a parametric approach that you can try. So often, I mean, you have some domain knowledge about your problem, which tells you something about the noise statistics. And well, then you have just a distribution function with a couple of parameters, usually, which you can predict. So here it's just a Gaussian distribution, so I can predict the mean and variance. The mean, as it used to be. The variance, well, I can use basically the same regressor, so I didn't do any optimization, hyperparameter optimization. And you just can train it with a different target, namely the square of a deviation of the labels and the in-sample prediction for the mean. And this way you end up with a prediction for a variance, and you can reconstruct the entire distribution from it, plot these error bands. Now it's symmetric. Here I should do some hyperparameter tuning maybe, or look what is going on there, but it's just for demonstration purposes. And yeah, I mean, it saves some CPU time. If you're on a large scale, you only need 2 fits, 2 predicts. Usually the fit is killing you if performance is killing you. But, I mean, there's a trade-off. I mean, you have made assumptions about the noise statistics. And they can be wrong, simply. So you put in some domain knowledge, but that domain knowledge often doesn't apply to some corner cases. So there's kind of a trade-off. So as for a solution I'm going to present, so the grocery store replenishment problem, we actually went for a parametric approach for these CPU time reasons. Plus, I mean, for these demand prediction problems, if quantities are sold in pieces, you can model this by gamma Poisson or negative binomial distributions, and you end up with 2 parameters. So these are 2 cases that are pretty much realistic, given the data that you usually get in such a case. So with the same mean, but different variance. So we run certain risks of selling quite a lot, if you see here in the second case, or selling almost nothing. So that can really happen in certain cases, but you can deal with it. If you use the right optimization, which now brings me to the second part of the data science pipeline, or the part I want to advertise a little, I would say, that people might build more often. So the algorithm is something I will explain a little bit in a reinforcement learning language. So this is not strictly reinforcement learning. I'm not about to optimize a chain of actions, but only the next action. So the next order we're going to make for a certain product. So basically what we do is we have now these probability distributions at hand for each day. And this allows us to propagate our state. So the state in this example is just the amount of goods you have in the store. So this inventory level basically. And this allows you to calculate the overall costs, or -1 times the return, as a function of the potential actions like this. And yeah, then it's just quite a simple minimization problem. So what I like about this method is that it's completely retraceable. So I can show you some kind of a little movie, how the states evolve. So this is the example of the first probability distribution I've shown you. So you end up, you start in a state where you have just a sharp distribution. You know how much you have in the store, right? As of now. If you go one day into the future, this broadens. If you go one more day into the future, so more goods come in, and it broadens further. And a third day, it has even broadened further. So if you look here, and if you say, okay, what would have happened if I had used a point estimator? So if I had predicted, for example, the demand is going to be 42 as an exact number, well, I would have ended up with just a single bin here with a probability of 1, which kind of seems a crude approximation if I look at this plot here. So what do we do with it? Well, now we can really optimize the costs or optimize the return. So there's going to be kind of negative immediate rewards for 2 sides to the problem. One side is that we just run out of goods, and the other side is that we have just too many goods in the store. and that these things have to be thrown away. For example, the bananas are brown. So, and this is like this branch of a cost function, and too low availability is the other branch of a cost function. And you can, this is just a convex problem, and you have a unique minimum. And this is your action that you can recommend. So let me fiddle around a little bit with the dispersion, or with the probability distribution for the demand, and assume that it's a little higher. So this is the scenario that you've seen just before, and this is a scenario which is more uncertain, for example, to uncertain weather conditions. And what you observe is that the function you want to minimize at the end of the day looks quite different. So the costs here are higher in this more uncertain scenario, which reflects that you have higher risk in general, and you want to do the least evil, so to say. And most importantly, also your action is quite different, depending on the uncertainty that you have. So this brings me to the question, well, could I go back to the scenario and where I have a point estimator and pretend I have zero uncertainty? And if you do it like that, you might end up with a cost function that looks like this. So it's completely flat here, and it doesn't matter really what action you take, as long as it is not too extreme, like these high quantities. So basically, when you would end up, excuse me, with a business rule, more or less, or a human decision, just trying to make sense of this optimization. So you would kind of completely lose the value your machine learning algorithm has generated. So, and for me, this is a clear point that, or for us applicators, that definitely for many applications that really make their way from the lab to the machine room, we need an optimization. We need to go beyond point estimators. And as data scientists, we also need to communicate that the optimal action at the end of the day essentially depends on the uncertainty we can predict. So, this is it basically. I just would like to say, Beyonder has a booth here. So we also have other products, for example, price optimization. And we're also hiring.
Well, thank you, Stefan. We have plenty of time for questions, and
so I didn't quite understand, when you've got the propagation of your probabilities ahead days into time, are you doing like a resampling algorithm there, or how are you actually propagating that into the future?
It's more or less, you can just write it down in exact equations and put that equations into Python code in principle. So it's just convolution integrals, basically.
So please, another question. So, okay, if there is no any other question, let's thank the speaker again.